Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Have you ever wondered, what if we could bottle the power of the sun, not with solar panels, but by mimicking the very process that sustains life on Earth? Imagine a world where a single sheet of material, no thicker than a leaf, could soak in sunlight, sip water from the air and breathe out clean fuel. No pollution, no smoke, just sunlight in and energy out. A future where your home could generate its own fuel the same way a tree grows its leaves. Sounds like science fiction. It's not. This is the extraordinary quest for artificial photosynthesis, revolutionary frontier where biology, chemistry and nanotechnology converge in a race to recreate nature's most elegant energy solution. And the stakes. Nothing less than the survival of our planet's climate and energy future. Photosynthesis is the ultimate solar technology. For billions of years, plants, algae, and cyanobacteria have used sunlight to drive a series of incredibly efficient chemical reactions, splitting water molecules, fixing carbon dioxide, and synthesizing the sugars that feed nearly every living creature on Earth. But here's the twist. Despite all its brilliance, natural photosynthesis is not particularly efficient by industrial standards. Most plants convert only about 0.5% to 2% of the sunlight they absorb into usable chemical energy. That's fine for a tree, which grows slowly over years, but it's far from ideal for a society hungry for fast, large-scale energy solutions. That's where artificial photosynthesis comes in, our attempt to take nature's blueprint and dramatically improve upon it using cutting-edge science. Unlike solar panels, which convert sunlight into electricity that must be stored in batteries, artificial photosynthesis turns sunlight into chemical fuels, substances like hydrogen, methanol, or even gasoline equivalents. These fuels can be stored, transported, and burned or used in fuel cells to produce electricity on demand. That's a game changer. It offers a way to store solar energy long-term, smoothing out the unpredictable supply that makes renewable energy so difficult to manage on a global grid. And more than that, it creates fuels that can potentially replace oil, gas, and coal without extracting carbon from beneath the Earth's surface. To grasp how this might work, we need to understand the basic process being mimicked. In natural photosynthesis, sunlight excites electrons in pigment molecules like chlorophyll. These high-energy electrons are then used to split water into oxygen, protons, and electrons. The electrons and protons help reduce carbon dioxide into glucose and other carbohydrates. Oxygen is released as a byproduct. In artificial photosynthesis, the goal is similar, but instead of making sugar, scientists aim to produce more useful, high-energy molecules like hydrogen or carbon-based fuels. The process typically involves three major components: a light absorber, usually a semiconductor, a catalyst for water oxidation to produce oxygen, and a catalyst for fuel production to generate hydrogen or carbon-based molecules. Early breakthroughs came in the 1970s, when Akira Fujishima and Kenichi Honda discovered that titanium dioxide, when exposed to ultraviolet light, could catalyze the splitting of water. This became known as the Honda-Fujishima effect, and it kicked off an entire field of research. Suddenly, the idea of using semiconductors to trigger chemical reactions with sunlight wasn't just theoretical, it was observable. But titanium dioxide only absorbs a tiny fraction of sunlight in the ultraviolet range. Researchers needed materials that could absorb the broader visible spectrum, which makes up over 40% of solar energy. That launched a decades-long search for better light absorbers. Materials like silicon, gallium phosphide, cadmium, sulfide, and perovskites each brought new possibilities and new problems. Silicon is abundant and absorbs light well, but it's prone to corrosion when exposed to water. Gallium phosphide has the right energy levels for splitting water, but it's expensive and unstable. Cadmium sulfide is efficient but toxic. Perovskites are cheap and tunable but degrade quickly in air or moisture. Every material that shows promise in one category, light absorption, catalytic ability, durability, cost, seems to fall short in another. Meanwhile, the catalyst side of the equation has seen remarkable progress. For the oxygen evolution reaction, which splits water molecules and releases oxygen, Catalysts made from iridium and ruthenium oxides have proven highly effective, but these are rare and expensive metals. The goal is to find alternatives made from earth-abundant materials like nickel, cobalt, or manganese. On the fuel production side, platinum is the gold standard for hydrogen generation, but again, cost and rarity make it unsuitable for global deployment. Researchers are developing synthetic catalysts with molecular structures designed to mimic natural enzymes, such as hydrogenases, that can generate hydrogen efficiently at low energy costs. Some labs are even merging biology and engineering to create biohybrid systems. These devices integrate proteins or even entire photosynthetic organisms with man-made components. In one project, bacteria genetically modified to produce fuel are tethered to semiconductor surfaces that provide them with solar power, like tiny living factories running on sunlight. In another, photosystem proteins extracted from spinach are wired directly to electrodes, capturing electrons as they flow through the protein and redirecting them toward fuel-forming reactions. This approach merges the exquisite molecular design of nature with the scalability of modern materials science. Yet the most visionary concept may be the so-called artificial leaf. First demonstrated in 2011 by Harvard chemist Daniel Nocera, this device uses a silicon wafer coated with catalysts to split water into hydrogen and oxygen using only sunlight. Drop it in a jar of water under the sun, and bubbles rise. Nocera's team later improved the device by coupling it with genetically modified bacteria that consume the hydrogen and carbon dioxide to produce liquid fuels. This two-stage system comes tantalizingly close to replicating the entire process of photosynthesis, from sunlight to fuel, without any of the organic machinery of a plant. Still, challenges abound. Efficiency remains low compared to traditional photovoltaics. Stability is a constant battle. Light, water, and oxygen are unforgiving enemies to delicate molecular structures. The integration of all components, light absorber, catalysts, electrolyte, and gas collection, into a single durable system remains a work in progress. And the biggest hurdle of all, scaling. A system that works in a beaker might fail completely when built to the size of a solar farm. Costs need to fall dramatically before this technology can compete with fossil fuels or even wind and solar power. And yet, the vision persists, because the potential is too enormous to ignore. Artificial photosynthesis, if fully realized, could transform deserts into fuel farms. It could offer a lifeline to communities without electricity grids. It could power ships, planes, and industrial machines with clean-burning fuels made from air, water, and sunlight. It could literally pull carbon from the atmosphere and turn it into energy. No mining, no drilling, no pipelines, just chemistry, sunlight, and human ambition. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. It was the summer of 1971 when a quiet revolution began. Not in a gleaming high-tech lab, but in the modest, humid corridors of the University of Tokyo. There, under flickering fluorescent lights, a young postdoctoral researcher named Akira Fujishima made a discovery so unexpected, so quietly profound, that it would go on to ignite a new branch of science. Working alongside his mentor, Kenichi Honda, Fujishima had been experimenting with a simple setup, an anode made of titanium dioxide, immersed in water, connected to a platinum cathode and exposed to ultraviolet light. Nothing flashy. Just electricity, water, and a beam of sunlight filtered through a quartz window. But then, bubbles. Tiny dancing bubbles of oxygen and hydrogen. Fujishima had unintentionally split water using sunlight, a process nature had perfected over billions of years, and no human had ever replicated with pure inorganic materials. This was the birth of photoelectrochemistry. The Fujishima-Honda experiment proved something stunning, that a semiconductor could absorb light and use the resulting energetic electrons to drive a chemical reaction. It wasn't just water electrolysis. It wasn't just a solar panel. It was quite literally artificial photosynthesis, though the name wouldn't be coined until decades later. The scientific community was intrigued, if cautiously. At the time, solar energy research was considered fringe, a curiosity for chemists with too much time and not enough funding. The oil crisis of 1973 changed that almost overnight. Suddenly, the idea of using sunlight to make fuel didn't seem like a distant dream. It seemed like a necessity. As the 1970s gave way to the 80s, the quest to improve on the Fukushima Honda cell began in earnest. In California, Stanford researchers started testing other semiconductors, materials like iron oxide, known commonly as rust. It turned out rust could absorb visible light and was both cheap and abundant, but it was also inefficient, prone to surface recombination, where excited electrons and holes cancelled each other out before they could react with water. In Germany, scientists experimented with gallium arsenide and indium phosphide, semiconductors, with excellent light absorption but devastating toxicity. These early years were a mix of optimism and frustration, with each promising material revealing fatal flaws. Then came a shift, not in materials, but in mindset. Instead of searching for a perfect semiconductor that could do everything, researchers began thinking modularly. Could one material capture light, another conduct electrons, and a third catalyze the reaction? This new philosophy mirrored how plants work. Photosynthesis doesn't rely on a single molecule, but a highly orchestrated complex of pigments, proteins, and membranes. By the late 1980s, labs in the US, Europe, and Japan were experimenting with multi-junction photoelectrochemical cells, layered systems where light absorbers and catalysts worked in tandem, like artificial chloroplasts engineered from the ground up. Yet, even as the technology progressed, funding remained sporadic. Fossil fuels were cheap and artificial photosynthesis was difficult. Breakthroughs were often incremental, a new catalyst that required slightly less energy, a new coating that extended the lifespan of a light absorber. The dream was alive, but it moved forward in slow, careful steps. It wasn't until the early 2000s that things truly began to accelerate. With growing concern about climate change and a renewed global interest in clean energy, artificial photosynthesis leapt from the fringes into the spotlight. Research institutions like the Joint Center for Artificial Photosynthesis, JCAP, established in 2010 by the US Department of Energy, were tasked with achieving the impossible: build a complete artificial photosynthetic system that could split water and reduce carbon dioxide using only sunlight. And here, finally, the pieces began to fall into place. JCAP's early work focused on materials discovery, using high-throughput screening to test thousands of potential light absorbers and catalysts. Their findings were shared publicly, creating a global database that allowed scientists everywhere to build on each other's discoveries. Simultaneously, private institutions like Caltech, Harvard, and MIT began exploring bio-inspired systems. Daniel Nocera's artificial leaf, first unveiled in 2011, was a culmination of decades of foundational research. His device used a silicon solar cell coated with custom catalysts to split water into hydrogen and oxygen. But Nocera didn't stop there. He took it further by introducing living bacteria into the system, bacteria that consumed the hydrogen and carbon dioxide and converted them into liquid fuels. It was no longer just artificial photosynthesis. It was synthetic biology fused with solar chemistry. The brilliance of these breakthroughs wasn't just their technical complexity, it was their elegance. Scientists were no longer just trying to replicate what nature did. They were beginning to do it better. Unlike natural photosynthesis, which is limited by the efficiency of biological enzymes and the need to support living cells, artificial systems could operate under harsher conditions, with higher energy densities, and without needing to feed or protect themselves. Imagine a photosynthetic panel that works 24 hours a day, every day of the year, producing hydrogen fuel with 10 times the efficiency of a tree leaf, without ever needing sunlight to grow or nutrients to survive. Still, these systems were fragile. Many catalysts corroded within hours, light absorbers degraded under heat or oxygen, Real-world conditions, dust, humidity, salinity, proved brutal. That's when material scientists and engineers joined the effort in full force, designing protective layers, self-healing coatings and new geometries to preserve functionality in harsh environments. Nanostructured electrodes mimicked the intricate shapes of leaf veins. Surface chemistry was tuned at the atomic scale to speed up reactions and reduce energy waste. Entire disciplines, catalysis, optics, materials engineering, were mobilized. To answer the question, how do we scale a miracle? There's something poetic in how the story of artificial photosynthesis mirrors the very thing it seeks to imitate. Just as photosynthesis evolved over billions of years from primitive cyanobacteria to lush green forests, the scientific pursuit has grown from simple beakers of water and titanium dioxide to sophisticated hybrid systems capable of feats unimaginable a generation ago. Yet like evolution itself, the journey is far from over. Every advance reveals new questions. Every success leads to a new frontier. And perhaps that's the most thrilling part. That somewhere in a lab bathed in morning light, a young scientist might be peering through a microscope, watching bubbles rise from an electrode and realizing they've just taken the next step in humanity's greatest energy adventure. Close. Your eyes and picture a field, not of grass or wheat, but of shimmering panels stretching across the desert, each one alive, not just capturing sunlight like a solar panel, but transforming it, molecule by molecule, into usable fuel. There's no whirring generator, no smokestack, no buried oil pipeline, just light, water, and air. This isn't science fiction, it's the next chapter in the quest for artificial photosynthesis, and the technology driving it is even more mind-blowing than the dream. Let's pull back the curtain and dive deep into how this miracle of modern science is actually supposed to work. At its core, artificial photosynthesis aims to do what green plants do every day: use sunlight to convert carbon dioxide and water into energy-rich molecules. In nature, that molecule is glucose, but in artificial systems we're aiming for something more practical: hydrogen fuel, methanol, or even synthetic gasoline. The challenge? Nature had billions of years to refine her machinery. We've had barely 50. So how do we mimic such an intricate process? First, we need something to absorb sunlight. That's where semiconductors come in. Materials like silicon, tungsten diselenide, or bismuth vanadate. When light hits these materials, it knocks electrons loose, creating an electrical current. But instead of using that electricity to power, go home like a solar panel does, we direct those electrons into a chemical reaction, one that splits water or reduces carbon dioxide. It's a solar-powered chemical plant at the nanoscale. But here's the trick. Sunlight alone isn't enough. You need a catalyst, something that can speed up these reactions without getting used up in the process. In plants, this role is played by enzymes embedded in the thylakoid membranes. In artificial systems, we use metal-based catalysts like cobalt phosphate for oxygen evolution or nickel-molybdenum-zinc alloys for hydrogen generation. Some are even based on abundant materials like iron and manganese. These catalysts are critical. Without them, the reactions crawl along at glacial speeds, wasting energy and time. Now imagine building a sandwich out of all these components. On one side, a light-absorbing semiconductor. On the other, a catalyst layer in between, a charge transport layer, an interface that moves electrons to the right place at the right time. This layered architecture is often engineered at the nanometer scale. Thinner than a human hair, more precise than a laser beam. The structure must be optimized not only for energy conversion, but for durability, water exposure, temperature resistance, and chemical stability. It's like building a space shuttle on the head of a pin and asking it to run forever. One of the most promising recent breakthroughs in this field came from the University of Chicago in 2023. A team of researchers developed a new photocatalyst based on perovskite, a crystal structure already famous for its role in next-generation solar cells. When coupled with a copper-zinc alloy and coated in a layer of molecular carbon, this device could turn carbon dioxide and water into ethanol with unprecedented efficiency. And it ran for over 100 hours without degradation. That's a big deal. Previous designs would corrode, collapse, or simply stop working after a few hours. Meanwhile, in Germany, the Helmholtz Association has been working on what they call solar fuel reactors, small modular units designed to sit next to water sources and generate hydrogen using concentrated solar power. These reactors use high-temperature thermochemical cycles, mimicking volcanic chemistry, to split water without any electricity at all. Just sunlight and smart materials. It's a different flavor of artificial photosynthesis, and it shows how diverse the strategies have become. But not every approach is purely synthetic. Some scientists are looking to biology for inspiration and even partnership. In 2022, a team at MIT unveiled a hybrid system combining silicon light absorbers with genetically engineered bacteria. These bacteria, fed a steady supply of solar-generated hydrogen, could then convert carbon dioxide into isopropanol, a common alcohol used in disinfectants and fuel additives. Think about that. We're feeding sunlight to microbes, and they're exhaling usable fuel. It's like farming the air. And speaking of microbes, there's another angle being explored called microbial electrosynthesis. These systems rely on electric current, generated from solar cells, to feed special bacteria that perform carbon fixation. Instead of using light directly, they outsource the energy collection to photovoltaics and let biology handle the hard chemistry. This kind of division of labor approach allows us to use well-established solar technologies while tapping into the efficiency of living organisms. But with so many directions, the field is facing a classic question: which path leads to scale? That's where pilot projects come in. In the Netherlands, a startup called Sun Hydrogen has deployed test arrays of photoelectrochemical cells in outdoor conditions to see how well they perform in real-world sunlight. In California's Mojave Desert, a company named 12 is building a synthetic fuel factory powered by renewable electricity and carbon dioxide pulled directly from the air. They're not using photosynthesis in the strictest sense, but the goal is the same: light in, fuel out. Governments are paying attention too. The European Union's Sun2X initiative is funding dozens of artificial photosynthesis prototypes aiming to produce jet fuel, ammonia, and even plastics from sunlight and air. In Japan, Toyota is backing artificial photosynthesis research as part of its long-term strategy to replace gasoline with hydrogen. The reason? If artificial photosynthesis works at scale, it could decarbonize entire industries. Not just cars and planes, but agriculture, chemicals, and power generation. But don't be fooled into thinking the challenge is solved. We're still dealing with efficiency plateaus. Most systems convert only 1 to 5% of sunlight into fuel, far below the theoretical maximum. Scaling the tech from lab benches to megawatt-scale systems is a logistical and engineering nightmare. We need to build devices that last not just for days, but for decades, in unpredictable climates, without rare or toxic materials. And even, if we get that right, how do we store the fuel, transport it, integrate it into global supply chains? These are real thorny questions. But the progress we're seeing today, across physics, chemistry, biology, and engineering, is the strongest sign yet that we might be approaching a tipping point. A moment when sunlight becomes not just a source of electricity, but a direct source of fuel, powering planes, factories, even cities. The day artificial photosynthesis becomes practical and widespread is the day humanity begins its departure from the fossil fuel era for good. And yet, this quest raises an even deeper question. What happens when we don't just harness nature, but begin to surpass it? Let's pause for a moment and imagine the world of the future. Picture a city glowing under the light of a setting sun. Alongside towering skyscrapers, streets are lined with solar-powered hydrogen stations, each one producing fuel directly from the air. No more oil rigs, no more pipelines, no more power plants belching smoke into the atmosphere. Instead, streets are alive with the hum of energy that comes straight from sunlight, sustainably, cleanly, and efficiently. This isn't a utopia in the making, it's the potential future that artificial photosynthesis promises. But in this future, it's not just about the technology itself. It's about the profound ripple effect this technology will have on every corner of life, on geopolitics, on industry, on how we think about energy, and on how we interact with the very planet that sustains us. Right now, we live in a world where fossil fuels govern nearly every aspect of our existence. From the gas in our cars to the plastic in our phones, to the energy that powers our homes, oil, coal, and natural gas are entrenched in our lives. But this has come at an immense cost, not just to our environment, but to our political systems. The dependency on these resources has created a volatile global economy, one that is vulnerable to the whims of oil-producing nations and is causing immense environmental damage, from oil spills to climate change. What if we could break free from this? What if we could produce energy right here on Earth, locally, sustainably, and infinitely, using nothing more than sunlight, water, and air? This is where artificial photosynthesis comes into play. At its core, artificial photosynthesis offers a chance to democratize energy production. Instead of relying on large centralized power plants, energy could be produced at the point of need. Homes could generate hydrogen to power their fuel cells, or even supply clean drinking water through solar-powered desalination. Farmers could produce liquid fuels or fertilizers right on their farms, using the carbon dioxide from their own greenhouses or even from the air around them. Industrial sites could operate carbon-neutral production lines, harnessing sunlight to create everything from fuels to chemicals without producing harmful emissions. This is the promise of a decentralized energy revolution, where the barriers to energy production are reduced, and the very control of energy moves from corporate giants and governments to the individual. But as powerful as this idea is, it raises important questions. Who controls this technology? Who gets to harness it first? And how do we ensure it doesn't fall into the wrong hands? The implications of artificial photosynthesis extend far beyond the energy industry. They could also be a game changer for climate change. A major hurdle in the fight against global warming is the overwhelming amount of carbon dioxide already in the atmosphere. More than 40 billion tons of it are pumped into the air every year by burning fossil fuels. Artificial photosynthesis could be a tool for capturing that carbon, turning it into useful products like fuel or even food, effectively helping to reverse the damage that has already been done. Imagine pulling carbon out of the atmosphere and turning it into useful fuels, all while reducing our reliance on traditional energy sources. This could be the very tool humanity needs to meet the global climate targets set in the Paris Agreement, helping to slow global warming while creating new sources of energy and economic growth. This scenario also opens up new debates about energy accessibility. For decades, energy has been treated as a commodity, something that can be bought and sold, controlled by powerful corporations and governments. But artificial photosynthesis has the potential to shift that power dynamic. It could lead to a world where energy isn't just for the privileged few, but is accessible to all, especially in developing nations where access to electricity and fuel is still limited. Solar cells and electrolyzers are already being deployed in rural communities to provide access to off-grid electricity, and artificial photosynthesis could further empower these regions, helping them leapfrog over fossil fuel-based energy systems. In this sense, artificial photosynthesis doesn't just represent a technological breakthrough, it represents a shift toward energy justice. However, there are also serious risks and concerns. Any breakthrough that promises such massive benefits also invites ethical, political, and economic dilemmas. The technology could deepen inequalities if it's controlled by a few powerful entities that monopolize its use. What happens if only wealthy nations have access to the latest advancements in artificial photosynthesis? What happens when entire industries, fossil fuel companies for example, are left scrambling to maintain relevance in a world powered by sunlight? The transition to this new energy economy could be as disruptive as the Industrial Revolution itself, with far-reaching consequences for labor markets, international relations, and global security. Then there's the issue of environmental impact. While artificial photosynthesis presents an opportunity to reduce our carbon footprint, it also requires raw materials and energy to create the technologies themselves. Can we build solar reactors and catalysts at the scale needed without further burdening the environment. The mining of materials like cobalt, lithium, and rare earth metals, essential to the development of these technologies, has its own environmental and ethical concerns. The future of artificial photosynthesis will not only depend on its ability to generate clean energy, but on how cleanly and sustainably it can be produced in the first place. So, while the promise of artificial photosynthesis is tantalizing, we must be cautious as we move forward. This technology, like any powerful tool, must be managed with care. But even as we wrestle with these complex questions, the potential rewards are too great to ignore. Imagine a world where, instead of digging deep into the earth for the last drops of fossil fuels, we simply harvest the abundant energy of the sun, directly converting it into the fuels we need. A world where energy is decentralized, cleaner, more affordable, and more equitable. This is the world artificial photosynthesis could help create. And the journey there, it's only just beginning. We've walked through the possibilities, the science, the technologies, and the implications of artificial photosynthesis. Now it's time to look into the future, the horizon where this technology might actually become a cornerstone of humanity's energy system. What does that future look like? And how soon will we get there? To answer that, we need to step back and consider the two biggest hurdles we face: scalability and commercialization. The idea of artificial photosynthesis in theory is brilliant. Harnessing sunlight to create sustainable fuel, transforming carbon dioxide into useful products, all while helping to tackle the global energy crisis, sounds almost too good to be true. But here's the truth. Scaling this technology to the level needed to replace fossil fuels is no easy feat. Right now, many of the most promising technologies are still confined to the lab or are operating on a very small scale. The challenge lies in moving from these initial successes to something that can be mass-produced and integrated into our global infrastructure. Think about it. Today's solar panels can turn sunlight into electricity at an efficiency of around 20 to 25%, and they've taken decades to reach that level. Artificial photosynthesis, on the other hand, is still operating in the single digits, with the most efficient systems reaching just around 5% efficiency at best. That's not enough to make a real impact on the global energy market. But scientists are optimistic. With new advances in materials science, better catalysts, and more sophisticated designs, the efficiency of these systems is expected to improve significantly over the next decade. Some researchers believe we could see efficiencies of 20% or more within the next 10 to 20 years, potentially putting artificial photosynthesis on par with traditional solar technology. But even if we can achieve higher efficiencies, the next hurdle is cost. While the technology itself holds incredible promise, it remains expensive to produce. The materials required for photoelectrochemical cells, catalysts, and other components are still costly and, in some cases, scarce. The production processes themselves are often energy-intensive, and scaling up manufacturing to meet global demand is a monumental task. This means that while artificial photosynthesis might be able to produce energy in the future, it has to be affordable enough to compete with the global energy market, which is dominated by fossil fuels and large-scale renewable energy solutions like wind and solar. This is where economies of scale come into play. If we can figure out how to produce artificial photosynthesis devices more cheaply and more efficiently, by improving manufacturing methods, or by discovering new materials that are both abundant and inexpensive, then we could start seeing these systems deployed more widely. In fact, some experts believe that once the technology reaches a critical mass, the cost of production will drop significantly, much like how the cost of solar panels has plummeted over the past 2 decades. But there's more to it than just efficiency and cost. To truly integrate artificial photosynthesis into our global energy system, we need infrastructure. This means developing the pipelines, storage systems, and distribution networks to transport the fuel produced by these systems. We need the logistics to get hydrogen, synthetic fuels, or carbon-based products from the rural solar farms or artificial photosynthesis stations to the cities, factories, and homes that need them. This is a massive challenge that will require significant investment in new infrastructure. But it's not an insurmountable challenge, especially when we consider how much infrastructure was developed during the rise of the fossil fuel economy. But while these challenges may seem daunting, there's a growing sense of optimism among researchers and entrepreneurs alike. The momentum is building. Several companies, including startups like Sun Hydrogen, 12, and Lanza Tech, are already leading the way in scaling up artificial photosynthesis technologies. These companies are pushing the boundaries of what's possible, working on prototypes, pilot projects, and small-scale systems that could soon prove the concept on a larger level. The key to their success will be the ability to prove that artificial photosynthesis can be produced at a scale and cost that's competitive with fossil fuels and other renewable energy sources. So what's next? We're on the cusp of a revolution. With ongoing research, we may see the first commercial artificial photosynthesis systems in the next 5 to 10 years, systems that could start to power small communities, provide fuel for transportation, and even contribute to reducing atmospheric carbon dioxide levels. The next decade will be a critical period, one where we begin to transition from lab tests to real-world applications. The breakthrough moment may come when a major corporation or government-backed initiative decides to invest heavily in artificial photosynthesis, setting off a domino effect that drives the technology into the mainstream. But even as we look ahead, it's important to remember that this journey isn't just about technology. It's about the choices we make as a society. Will we embrace these new energy systems, pushing for cleaner, more sustainable sources of energy? Will we invest in the infrastructure needed to support them? Will we ensure that these technologies are accessible to everyone, not just the wealthy or the technologically advanced nations? Artificial photosynthesis has the potential to transform everything, from how we generate energy, to how we interact with the environment, to how we think about sustainability. It could be the key to reversing decades of environmental harm, while simultaneously ushering in a new era of clean, sustainable energy. But as with any great revolution, the road to widespread adoption will be filled with challenges. We will have to confront not only technological and economic barriers, but also social, political, and ethical issues that could shape the future of this transformative technology. This is more than just a scientific breakthrough. It's a chance to rethink our relationship with the planet and with each other. As we stand on the precipice of a new energy era, we must ask ourselves, what kind of future do we want to create? One thing is certain, the quest for artificial photosynthesis is not just about harnessing the sun's power. It's about redefining how we live, how we consume, and how we sustain ourselves as a species. The question is, are we ready to embrace that future? If you're excited about the potential of artificial photosynthesis and the future of sustainable energy, then this journey is only just beginning. Let's continue exploring the mysteries of the universe together. Hit that subscribe button, like, and share this video. And most importantly, drop a comment below. What do you think? Could artificial photosynthesis be the game changer we've been waiting for?